Let's solve this system of differential equations. We have x prime equals negative 5y and y prime equals 2x plus 2y. I'm going to be using the eigenanalysis method to solve this problem, but before I get started, I always like to rewrite the problem into a form that is a bit more pleasant for my eyes. This is the formula that I'm trying to write up, right? X prime equals ax. That's what we're gonna break out from here. So here we don't have an x, so I'm gonna include a 0 times x. There it is. And turn this into a matrix form. X prime y prime equals my matrix A, 0, negative 5, 2, 2, and my matrix x and y. Next step, we need to find our eigenvalues. This is what we need to determine. The determinant of a minus lambda I equals 0. To calculate this, we're gonna plug in our matrix A and subtract lambda on the diagonal. To find the determinant, we're gonna multiply this times this minus this times this. That's what you see right here. Clean it up and simplify. We can find the quadratic equation of lambda squared minus 2 lambda plus 10 equals 0. Now the roots of this equation is lambda 1 and 2 equals 1 plus minus 3i. We have complex conjugate roots. Alpha is my real part, beta is my imaginary part. Now we need to determine our eigenvectors, but since we have complex conjugate numbers here, therefore we're gonna have to calculate only eigenvector for one of the eigenvalues, and from that we'll be easily able to determine our second eigenvector since complex conjugates. We'll see that when we get there. First things first, let's find our first eigenvector corresponding to our first eigenvalue. This is the formula that we need to follow. A minus lambda I times the x vector equals to the 0 vector. That's what we can see right here, filled in. My A matrix minus lambda I on the diagonal, this value substituted into our lambda. Our x vector is my x1 and y1, and the 0 vector is 0, 0. Take this, transform it into equation form, and we can see right here and right here. This times this plus this times this equals 0. Same thing over here, this times this plus this times this, we have it right here, equals to this 0. Now, I need to determine if these two are multiples of each other. Therefore, I'm going to multiply this equation by the conjugate of this piece. You can see it right here, negative 1 plus 3i. And I'm going to multiply this equation by negative 5. This term times this term, I wrote it out right here. We can see that it's going to give us 10. That's what's there. And these are the results of these multiplications, and from these two we can see that this equation is practically the multiple of this equation. If we add this to this, we can see that this equation completely disappears. That's good for us. We can only work for this one. Take this equation and we're going to solve for x1. x1 equals negative 5 plus 15i over 10 y1. I'm going to simplify it by a 5 and I'm able to get x1 equals negative 1 plus 3i over 2 y1. Now at this point we know that the possibilities are that we have infinitely many solutions. Therefore, we're simply going to pick a value for y1 equals 2 You could pick 1, 2, 3, a million, whatever. Pick something that's not too crazy. I'm gonna pick 2 because if I plug it in, my x1 will simply be minus 1 plus 3i. At least I get rid of that ugly division. Okay, this and this. We have them determined. Now I'm gonna write up my eigenvectors. And remember, these were my eigenvalues. Therefore, the plus minus, we're gonna take advantage of it. And when we write up our eigenvectors, negative 1 plus 3i, I'm gonna put it as negative 1 plus minus 3i. Therefore, we're able to find both of our eigenvectors and we don't need to do this whole calculation again, right? And y1 equal to, that's what comes right here. Now, from here, I'm gonna separate my real part vector and my complex, the imaginary part vector. So I'm gonna have negative 1 and 2 plus minus, I'm gonna leave the I in the front, and I'm gonna have 3, and over here the imaginary part is gone, so therefore 0. So 3, 0. I'm gonna designate negative 1, 2 as my u vector, and 3, 0 as my v vector. And to finish up the problem, we're able to write our general solution right here. This is the formula that I'm following. Let me read it out just in case you guys can't see. C1 times e to the t. Here we had an alpha, which is our eigenvalue, right? But that is a 1. Therefore, it's just 1. Right here, see? So 1t times cosine 3t. The 3 comes from right there, my beta, just like the formula says. I'm following this purple formula. For my u vector, simply plug in the u vector, minus sine 3t, 3, 0. This is my v vector, right? What we found right there. And the second part, plus c2, e, again to alpha t, but alpha is 1. Cosine 3t, 3, 0, plus sine 3t, negative 1 and 2. Now, remember, don't get scared if you see the general formula looking a little bit different from one person to the other one, because here it is very person dependent. If you pick a different value for this one, this will look completely different, right? Therefore, this will continue transferring down through the problem and their solution is gonna be different as well. But at the same time, the general structure of the solution will not change. We will have the constants, the e, to the power of the alpha t, and the cosine signs, and the vectors, those will be the same. All right, thank you for watching. Please give a like to the video so everybody else can find it as well, and have a good day.